Hey guys, this is Hiraku Murakami with NovaEdge Academics. Today we'll be continuing with topic C3, wave phenomena. This is part 2 of the video and we're going to start off with diffraction. So until last video we covered reflection and refraction and critical angle. This time we're talking about diffraction, which is spreading of wave. And the spreading of wave can happen when you go through something called an aperture or like an opening. So in this case, like the ocean wave, it hits this coastline where there's only one opening, then it's going to start spreading out like a ripple. Okay, and this spreading out phenomenon is called diffraction. Now, how much waves diffract depends on the wavelength, so the distance between the wavefronts, and also the aperture width. This is something that we'll be exploring more in detail in HO topic, so it's not for SO topic. However, just one thing to note is that this diffraction can only happen when the aperture is around the same as a lambda, if not smaller. Okay, so this is really important. So another prime example of real life is sound. Sound can also diffract pretty well, actually. So in this example, when Jill is, let's say, screaming at Jack, right? So the sound is going to the doorway. It's actually spreading out to Jack, and that's why Jack can hear Jill, even though direct line-wise, there's a wall in between that prevents Jack from hearing anything, okay? Now, you might say, okay, but, across rooms I can hear people, but that's just penetrating through the wall, so that's something else. However, the moment I close the door, the sound that Jack hears goes down a lot, right? So that's the effect of diffraction, which is you can hear the sound even though you're not in a direct line. And you might be like, okay, well, sound is a wave and it diffracts. How about light? Can light diffract? The answer is yes. It's just that this doorway is too big. So this doorway has to be way smaller. In fact, it has to be nanometer scale for us to be able to see this light diffraction. Okay, now this would be scary if light can diffract in real life in terms of like not lab setting, like nanometer setting, but in real life, because if I replace the sound with light and it actually managed to diffract across the doorway, this actually means that Jack would be able to see Jill because light is diffracting into his eyes, right? So Jack would be able to see Jill even though they're not directly in line of sight. Okay, so just something to note. So there is a relationship between wavelength and aperture that you need to take into account whether or not diffraction is happening or not. Now, before I go into another example, which is like really prime example of diffraction, I need to talk about superposition. So superposition is a phenomena where waves can add one another. So, in terms of amplitude, they can add on top of each other. So as an example, if I have a wave like this and a wave like this coming together, then they will form a big chunk when they come in contact, and they're just gonna keep going, right? You might be asking, okay, what if I flip this? What if I had like this? What happens then? Well, you asked the right question, because the next one was about this one and it cancels out. This guy cancels out. And then after that, it continues. Now this canceling out effect, we call that destructive interference because they're destroying each other, right? The other one, we call it constructive interference because they're constructing each other. They're adding on top of each other. This is a really, really important distinction, okay? So pause the video and give this problem a try. So I actually have a hack for this. It's just tracing them and combining them. So in this case, I combine them. Okay. And so what overlaps is canceled out, and what remains is something like that. So that's the answer. Okay. They can throw at you a lot of different types of problems like this in paper 1 for physics. So just do practice problems, things like this, and make sure you're familiar with it. Now I'm going to talk about something called double-slit interference, and it's actually called Young's double-slit experiment. So in a lab setting, he wanted to diffract light, and he wanted to see what happens then, especially if there's two of them and they interfere with each other. So as an example, he's going to have light. By the way, those are the wavefront, so this is lambda, and he's going to have two slits in nanometer scale, by the way. Okay, so two slits. What happens? Well, they're going to diffract like this, and this guy's going to diffract like this. And so they're going to interfere each other. In fact, let me just a better picture. It looks like this. Now, it is mesmerizing. It is quite confusing, right? But there's one thing that I want to highlight, which is that wavefronts, I told you wavefronts usually is where crest is, where the peak is. So if their wavefronts are touching each other, that means the max of this wave and the max of this wave are touching, meaning they constructively interfere each other. They add up to each other. Okay? So in this case, let me put the dots. Wherever they're touching each other is constructive interference. In fact, I can make a line out of this, right? I can do the same thing for the next one. So again, same thing, this side. That's pretty cool. There's a pattern that we can actually start to see. And you might be saying, okay, what about the other one, the destructive interference? Does that happen? It does. Those are the points where one wave is max and the other is minimum. So we actually only see one line. In fact, that's actually right in between them. Okay, so the red one is where destructive interference happens, and the black one is where constructive interference happens. And why do we like this pattern? Because pattern means it's something we can mathematically model or calculate or predict, right? And so if I were to actually draw like the intensity pattern, it looks something like this. So we have max here, minimum here, max, minimum, like that. Which means, in other words, I'm actually going to see light here and no light here, because those are where destructive interference happens. And this is actually what was observed when we did this double slit interference experiment, Young's experiment. So these two slits produced this strange looking pattern. Okay, now there is a mathematical model that we can use. I'm going to move on to the next page, which is this. This is the equation that you need to be a master at, especially if you're SL, because HO, we have other things that they will test on, but SO, this is the maximum they'll test you on. And so let's dissect what these are. So S is actually the distance between two consecutive bright fringes. So it's here, right? D, small d, is the distance between the slits. Big D is the distance to the screen. And lambda, of course, is the wavelength. So if I have light coming in, the distance between the two wavefronts is the wavelength. And this relationship holds true for IB physics context. And so you need to be a master at using this. And so let's do a prime example. So pause the video and give this one a try. So they actually give us a wavelength. The wavelength is this. They also give us the double slit separation, which is D. By the way, I'm changing everything to meters, okay? They also told us that the fringes want to be at least this much. The distance between fringes is this. Okay, so let's determine the distance. This is the answer, part B. Okay, so she's saying that we want to keep all the positions the same, but she wants to change the fringe pattern. Okay, so positions are the same, so both D's are the same. She wants to change the S. We want to increase S. Well, the only way to do so is increasing wavelength. But how do we increase wavelength? Well, we actually need to change the color. We need to change the color from green to red, because red is like 750 nanometers. Green is somewhere in between. And if we want to make the fringes narrower, we need to make it into violet. Violet is 400 nanometers. Okay, now this spectrum, I've already covered this in topic C2 in the previous videos. So if you are confused about that, then go check that out. But this spectrum is in your data booklet, so you actually don't need to memorize. Just know how to use it when it's relevant. Okay. Now, last but not least, I'm going to talk about something called path difference. So in the double slit experiment, we found a pattern, but there's actually another way to discern whether something is constructive interference or destructive interference. And that is just basically using the difference between the paths. So let's say I have two wave sources, wave source A and B. Same thing, I can model it as slits if I want. Doesn't matter. Now, what if I give you a random point P here? And I told you what kind of interference is happening. Is it constructive? Is it destructive? Is it somewhere in the middle? Well, there's a simple trick, and that is to find the distance between A and P and distance between BP. The difference is called the path difference. And if this is a multiple of a wavelength, because this is a wave, right? So there's a wavelength. If this is a multiple of a wavelength, then it's constructive interference. If it's multiple of n plus 1 over 2 times wavelength, then it is destructive interference. If there's anything that doesn't fit into those two, then it's something in the middle. Okay? Now you might be saying, okay, what is n? Okay, n, we call that the order. Okay, and the order, why? Because that corresponds to where the constructive interference is happening. So I'm going to go back to this one, actually this one. N in the middle is n equals 0 because, well, guess what? There is no path difference. They are isometric, right? So there is no path difference. Path difference is 0 times lambda. Now here, if I were to do it here, between this and this, then the path difference becomes 1 times lambda. Here is going to be 2 times lambda, 3 times lambda. Same thing, 1 times lambda, 2 times lambda, 3 times lambda. Anything in between here, that's also n equals 0 for destructive. So path difference is 0 plus 1 over 2 lambda, right? So n corresponds to where on this, basically the screen, it's going to end up, or in which order it is, okay? So let's do a practice problem. Now this one is a past IB paper, paper 1. Okay, so pause the video and give this one a try. This is the level that you should expect to be able to answer. So pause the video and give this one a try. Okay, so paper 1, the best strategy for paper 1 is to eradicate the options that are not true. So the first one we can eradicate is option A. Why? Because they told us that B is a constructive interference. B is a bright fringe. So it has to be path difference is equal to multiple of lambda, whether that is 1 times lambda, 2 times lambda, 3 times lambda, 4 times lambda, right? It cannot be 1.5 times lambda, so we can eliminate A. Okay, let's see if it's B, C, or D. Well, let's draw it out. They told me that there is 3 dark fringes in between. So let me draw this. That's a bright fringe, 1 dark fringe, 2 dark fringe, 3 dark fringe, and bright fringe at O. Okay? So that means that I am 0, 1, 2, third one. I'm at n equals 3. So at n equals 3, that's an answer of C, right? Path difference is 3 times lambda. Okay? We're going to finish here for SL content. Okay, so that was a past paper. Now, if you would like me to include past papers in our videos, or have a separate video where we solve past paper problems, if those kind of contents are interesting for you, then leave it down in the comments, because I won't know if those are what you're looking for in your education. So let me know down below in the comment section if you want me to cover more past paper problems. Okay, now for HO, there is a path difference for HO section, so stay tuned for the next video where we cover HO contents from path difference, single slit, multi-slit, diffraction grading, etc. Okay, so yeah, see you in the next video. Hey guys, thanks for watching. If you like this kind of video, then consider giving us a like and subscribing to our channel. We have a lot more lecture style video and content like this in our channel, so feel free to go check it out. If you're looking for additional guidances like one-on-one tutors in IB subjects, SAT, TOK essay, IAs, writing, etc., then go to our website at NovaEdgeAcademics.com, fill out the form, and we'll get in touch with us. In the meantime, we'll see you in the next video.